Okay, tonight I am going to talk about the science of 2020, 2021, including science of the pandemic. Even though I'm a scientist, keep in mind I don't know all sciences, but we'll save our questions and our discussion till after the meeting, okay? Okay, I know you've been hounded by the media about climate change, but you're only getting superficial information from the media. So I thought I'd start out with that. And the reason you're getting hounded is because the Intergovernmental Panel on Climate Change put out a report. And this is working group 1. There's like 8 or 9 working groups, and they put out one report after another over the next year, and they do that about every 8 or 10 years. We have acquired a lot more data over the last year and a half. They're doing a better job collecting data. And their conclusion was, things are getting worse. We are now 1.09 degrees centigrade warmer than pre-industrial times, which is about 2 degrees Fahrenheit. And most of that has come in the last 40 years. And this is an estimate of temperatures for the last 80 million years or so. And we are right about here now. And these lines that go up this way are scenarios based on what we do or don't do. This period right in here, between 30 million years ago and about 3 million years ago, is referred to as, by anthropologists, as the planet of the apes. This is the time period where mammals, and particularly primates, evolved quickly. And then they got cold, and they got cold because they think that there was some plant that grew and sequestered the carbon dioxide out of the air. And we've been basically in an ice age ever since. Fortunately, by 3 million years, the hominids had evolved, and they were a little bit more resilient. And I know our friend Bob is going to talk about that one day again. So CO2 is a major greenhouse gas that we exhale by breathing, and that we consume by burning fossil fuels. And if you have conservative friends, they're probably going to tell you that it's not an indicator of climate change. But I think in this case, and in most cases in the past, it probably is. Okay, 3 million years ago was the last time that we had this much CO2 in the air. We put 50 tons of CO2 every year into the air. We need to reduce our output, and we need to think about capturing carbon out of the air to prevent too much warming. Here's where we are right now. Here's where we've been for the last 800,000 years. So we've done quite a job putting carbon into the air. And this graph kind of shows the warming caused by CO2. So you can show that to your conservative friends. This is an estimate of the CO2 in the air. And you can see back during the planet of the apes, there was quite a bit of CO2 in the air, which is what kept it warm. So even if we do get to net zero by 2050, we're still going to warm up, probably more than the 1.5 degrees that they're talking about. Of course, planting trees is a good first thing to do because we've deplanted the planet, we've deforested our planet. And it's estimated that we can actually plant enough trees to suck up about 30% of our emissions. Now, if you guys drive through the neighborhoods, what do you see? Here and other cities as well. You see grass and a few trees. If you get everybody to plant a few more trees, it would help a little bit. Fortunately, we have a new president now. And if he can get funding for climate change, one of the things he wants to do is he wants to capture carbon. And I have a video here of how we can make a big difference capturing carbon.
Today, our planet's atmosphere contains more carbon dioxide than we've ever seen in human history. As one of the leading drivers of climate change, CO2 is a problem that's only getting worse. But what if we didn't have to choose between our economy and our environment? What if we could turn our carbon liability into an asset? The truth is, CO2 can be recycled into valuable products at a scale that can transform our global economy, but it won't happen on its own. The NRG COSIA Carbon X Prize is a $20 million competition to convert carbon dioxide into valuable products.
CarbonCure's technology takes CO2 and converts it into stronger and greener concrete.
Our process makes a very nutritious protein.
Carbon emissions to bioplastic.
Carbon negative biofuel.
Plastics and other sorts of materials.
Carbon nanofibers.
Feeds for fish.
We take carbon dioxide and water and we turn that into alcohol.
My motivation for competing in the Carbon X Prize is my son. What am I going to leave for him in 50 years, 100 years? What about his kids and their kids?
There's a sense out there that climate change can't be fixed. That's something that we just adamantly disagree with.
38 teams from around the world accepted the challenge. After 2 years of development and testing, judges have narrowed it down to these 10 finalists. Teams must scale up and demonstrate their technologies using emissions from real power plants. The finals will take place at 2 new test centers, one in Calgary, Alberta, and one in Gillette, Wyoming. The stakes have never been higher. Together, these solutions will help transform our economy and redefine our climate future. Imagine a world where everything around you is made from carbon emissions. From the products you use every day to the clothes you wear, to the roads you drive on, to the buildings you live in. Welcome to the circular carbon economy.
Alan is a professor at MIT, and Sahag is his graduate student. And they have come up with what they call their breakthrough. And this is a system to capture CO2. And I'll try to explain it to you as I show a little quiet video. So what they've done is they've come up with a chemistry that they bind to electric plates, to metal plates. And that chemistry, when there's electric charge put through the plates, captures CO2. And this little video is going to show the air flowing in, and the CO2 is the red molecules, and they're going to apply some electricity to the plates, and boom, all the CO2 goes to the plates. And this is the CO2 binding to the plates, the activated plates, the activated chemistry on those plates. So when you pass your air containing CO2 or even effluent out of power stations, the CO2, the red CO2 gets accumulated on the plates, and then you put a reverse charge on it and it comes off. So you can concentrate it and compress it from there. And this is a major breakthrough. I mean, I think this is a major breakthrough because it doesn't take a lot of energy. And it's reusable. In fact, currently, they say that after 7,000 cycles, it's still 75% efficient, and they're working to make it more efficient. This is a little company up in British Columbia, Squamish, British Columbia. They capture carbon using an older-fashioned, more energy-intense mechanism. But they use their carbon dioxide to make gasoline. And their dream is to have these little plants all over the place, making gasoline for local communities. And if they married their technology with this technology, they could probably make it cost-effective. Okay, we can't really capture enough carbon quickly to keep us from warming up substantially. So we're going to have to lower our emissions as well. And we know pretty much where the carbon comes from: electric production and transportation. Now, I think that the transportation, hopefully over time, is going to become more electric, so electric will take up a bigger portion of that. Fortunately, we do know how to produce electricity. But the sun doesn't always shine and the wind doesn't always blow, so we have to find a way to store it. So all around the world, these battery farms are popping up because we have our wonderful lithium-ion battery technology that can store energy better than anything that came before it. So we're thinking that batteries are going to do it for us. And this is kind of how it works. You put the batteries close to where you're producing electricity, and you take some of the electricity produced and charge the batteries, and the rest goes to the neighborhoods. This is a Tesla battery farm in Australia, and one of the problems with the current lithium-ion technology is that occasionally you get a fire. And you get a fire because the lithium-ion batteries that we currently use have liquid electrolyte solution in them that is flammable. And what happens is it heats up, it expands, it bursts, and it catches on fire. So the new technology coming out now is solid-state battery technology. But we're still kind of a ways away from it. Toyota developed a solid-state battery which doesn't have a liquid electrolyte in it. Quick charging is one of the characteristics of solid-state batteries, as well as size and weight and the fact that they don't catch on fire. So anyways, let's go back to Toyota. They're partnering with Panasonic, and who makes their batteries through Panasonic? Tesla. QuantumScape is the darling of the stock market. They're saying about 2025 for their solid-state batteries, and they work. Their solid-state batteries work. The question is, can they be scaled up? And guess who sits on the board of this company? Somebody from Tesla. Solid Power, that's the name of this company, Solid Power. Ford and BMW are partnering with them. And these guys have a path forward. Their technology works. But again, they have to figure out how to scale it up. This is a company called Prologium. They make small solid-state batteries for consumer electronics, and they've been selling these batteries already for 3 or 4 years. And you would be happy to have one of these batteries in your phone, because your phone wouldn't need charging very often, and the battery would be lighter weight, and it would charge in 10 minutes. Now they made a prototype of a car battery, and they say here it's 50% smaller, 20% lighter, and 30% cheaper than the Tesla Model 3 pack. Again though, when can it be produced in quantity? We don't know that. In the meantime, Tesla has constantly been improving their battery technology, and they filed a patent a year ago for a new battery, which is their 4680 battery, which is a bigger form factor, but it holds 5 times the energy. More importantly, perhaps, it's 56% less expensive to produce, and it's already being produced. So because of the fact that this battery is already going to be on the market, I think we should look at it and compare it to the solid-state batteries. A more energy power stored per weight, but not as much as the solid-state batteries are going to be. Better range, but not as much as the solid-state batteries are going to be. Less heat, less of a fire chance. They really put some engineering into this battery. But again, solid-state batteries aren't going to burn up as easily. Very quick charging, the same as solid-state batteries. 56% less expensive. That's the clincher right there. and it's in production. So being in a capitalist system, the cheap guy is going to win out right here for a while. And they built in recyclability. Now, I've told you tonight about just a few technologies that we can use against global warming, but there's a lot of stuff going on. There's a lot more stuff going on. So I'm confident if we don't have nationalistic governments pop up all around the world who don't want to believe in climate change, we should have it somewhat under control by 2050. The thing I worry about the most is that when people figure out that they can make products from the CO2 out of the air, and they can get the CO2 out of the air cheaper than they can get oil out of the ground, it's going to get cold. Now, space exploration also is in the news, but I thought it would be important to go through some of the major events that's happened in the last 2 years. SpaceX took the first Americans to the International Space Station in almost a decade. SpaceX is developing their Starship. And if you watch that development, it's amazing how fast they developed that. It's a huge ship. NASA has chosen SpaceX to use a modification of that Starship for the lunar lander. Also, the military has approached SpaceX because you could fit 100 Marines and their equipment into one of those ships and get it to anywhere on the Earth very quickly. SpaceX also did a high orbital tourist flight, almost fully automated, and the altitude was the highest altitude that humans have flown since the Apollo days. China brought some soil back from the moon. China has a Martian lander. They landed a Martian lander. China has a space station that they're building. United Arab Emirates has a Mars orbiter now. Now, to be fair, they didn't build it and launch it. They paid for someone to build it and launch it. Japan returned samples from the asteroid Ryugu, and there's a nice documentary about that, and it's very interesting to see all the issues they had to deal with. Blue Origin and Virgin Galactic get honorable mention. James Webb Space Telescope goes up in December, hopefully. This is going to make the Hubble look like a toy, and I'm very anxious to see that go up. As you know, Perseverance is up there, and its claim to fame is that little helicopter, but also they found organic molecules on Mars, and they're hoping to return some of the samples that they found on Mars. And they take beautiful pictures, and this is a picture that came back from Mars, and it looks a lot like veins of gold, and they very well could be veins of gold. And I know that everybody wonders why the billionaires are making their own space programs. And here's a little bit of information about that.
A gigantic 173-mile by 144-mile wide massive ball of metal. We want to introduce you to the M-type asteroid 16 Psyche. It's shaped like your standard potato. However, it's much, much bigger and made of stuff that is much more valuable. See, the reason that it is called an M-type asteroid is this. The majority of its composition is metallic, meaning that it is mostly made of metals like iron and nickel, commonly found here on Earth. But the metals don't stop there. Scientists have discovered that 16 Psyche is also comprised of mind-boggling amounts of gold and heaps of platinum. Just how much are these metals worth? Try this on for size. 16 Psyche, if mined, would yield 10,000 quadrillion dollars. That's 19 zeros, people. And planet. And due to the asteroid being not too far away, after all, it's located right between the orbits of Mars and Jupiter. It has already been announced that they will be able to launch a rocket in August of 2022, and the company behind the launch will be none other than SpaceX. Once up there, the real fun will begin, and by using a ton of incredibly advanced instruments, like a gamma ray and neutron spectrometer. we will get an even more detailed and accurate look at just what this giant golden potato is made of. Who knows? We may find that there is even more gold than we thought. But why stop there? Who is to say there couldn't be diamonds too? Diamonds! Diamonds, don't you see? But that doesn't mean that private investors and companies aren't interested in getting up there and taking a swing at the potato-shaped fortune. In fact, everyone's favorite billionaire, Elon Musk, not to mention the man behind SpaceX, has sent out some rather coy tweets hinting that he would be very interested in mining 16 Psyche. See, this idea is nothing new. The one that says there is a wealth of gold to be mined up in the heavens. In fact, there are two companies called Deep Space Industries and Planetary Resources that are backed by big-name celebs, and these companies are specifically geared towards mining and extracting gold from asteroids in our solar system. They've even been eyeing another asteroid, known as 2011 UW158 asteroid. And while it's nowhere near the levels of wealth contained on 16 Psyche, this floating gold mine is twice the size of the Tower of London and still worth an approximate $5.7 trillion. No wonder people are scrambling to get up there. Which brings us back to Mr. Musk, who, when asked if he would comment on the idea of him mining the gold in asteroids due to gold not having a fixed supply, he simply tweeted the word Psyche and linked to an article by Fox News stating the gold up there would make everyone on Earth a billionaire. Touché, Mr. Musk. Touché.
So if you're investing in precious metals, keep an eye on this. Starlink is the array of low Earth orbit satellites that will provide everybody with high-speed internet for $100 a month. And they are going hot, I think, this month. So they'll get my business because CenturyLink has had my internet off for a week. They turned it off by accident and they haven't come to turn it back on. So he might get my business. Okay, turning to some biological news. Statins. Everybody here should know what statins are. Yep. They lower your cholesterol, right? And statins have been the target of conspiracy theorists for a long time. Part of that is due to the fact that some people don't tolerate it very well, certain statins very well. And when you think about the brain, our brain uses a lot of cholesterol. It needs a lot of cholesterol. So it makes sense to think that if you're lowering cholesterol levels, you might screw up your brain. But it turns out the brain has its own mechanism for making cholesterol. But enough people have published, even doctors have published that articles that statins will cause dementia. So somebody got smart and did a study, a big study of about 140 to 50 people who were exposed, who take statins, and about 140 to 50 people who do not take statins. So I'm going to highlight some of this for you. So here on the top, these patients don't have any exposure. These are the number of patients that manifest with these diseases up here, okay? And this is all neurodegenerative diseases combined: Alzheimer's, unspecified dementia, multiple sclerosis, Parkinson's disease, and ALS, which is Lou Gehrig's disease. So as you can see here, the percentage of the patients who actually manifested with those diseases over about a 4.5, 5-year period. On this line here, this is with statin exposure. And you can kind of compare, like for all neurodegenerative diseases, 6.4% manifested over the period of 5 years with no exposure to statins, and only 3.6% manifested. And for Alzheimer's, which is the big name that the conspiracy theorists go after, 2.3% manifested without exposure to statins, and 1.1% manifested. So anyways, it looks like all across the board, you're safer on statins for neurodegenerative diseases, And the p-value, the statistics are down here, the p-value is the probability that the data could be random. The lower the p-value, the more solid the data is, and these p-values are 0.001, below 0.001, because the population was really big. And if you want to see it on a graph, this is what it looks like. And this is only over like 4 years, four and a quarter years. And you see how the untreated group takes off, gets way more neurodegenerative diseases. And I would like to see this go out 20 years and see what happens. But anyways, this is a good major breakthrough because, well, now we know that statins are associated with decreased incidence of these diseases. All the statins worked except for fluvostatin. So if you're on fluvostatin, ask your doctor for something different. There were some that worked better than others, but the best conclusion of this is that now we see that these things help prevent these diseases. If we can figure out what the pathways are and the mechanisms are, we might find new treatments for these diseases or more preventative measures for these diseases. And a bonus, if you're on statins, is you're less likely to get severely ill by COVID-19. Speaking of, okay, pandemic. You all should have learned some new terms during the pandemic. One of them being messenger RNA vaccine, monoclonal antibody, cytokine storm. So first off is the messenger RNA vaccine. This is the first time the FDA has approved a messenger RNA vaccine in mass like this, and we are all guinea pigs. But it's a really nice way to make a vaccine because instead of injecting a bunch of protein from the virus, you're just injecting a small snippet of messenger RNA. And as you know from biology class, Biology 101 in high school, is that messenger RNA produces protein. It's a message from the genome to produce protein. And in this case, they coat the messenger RNA in a lipid nanoparticle so it can bind to a cell. So they inject this into you. The messenger RNA gets in the cell, goes to the ribosome, and it makes the spike protein. And that's all it does, is makes the spike protein. And it does it a few times, and then it breaks down over time. And when you get immunized, you make the spike protein, and of course you make antibodies. Now let's talk about the old-fashioned way of making vaccines. You gotta remember now, vaccines are only able to grow inside of cells. They don't grow in culture by themselves. They don't divide by themselves. They have to be inside of the cell. Okay, so that makes it problematic. It always has made it problematic to produce vaccines because you have to grow in living organisms. So mostly we grow them in eggs and in tissue culture. And tissue culture is just growing them in cells that grow in culture and growing in fermenters. And sometimes we can attenuate the virus, which means that we make it less invasive so that you get an infective dose, but it doesn't make you really sick. Okay? Now with the messenger RNA vaccine, we can make that very simply and very quickly as a chemical reaction in a vat. And instead of getting a big mass of protein from the virus and sometimes from the cells that the virus was grown in, you're getting just one protein. You're going to make one protein. And the advantages of messenger RNA going forward is that it's more robust in many ways, but mostly because you can target the protein and you can make it very quickly. It's simpler, production is faster, facilities and equipment are much smaller. quick turnaround time. And what I like the best about it is that they can make multiple immunizations in one much easier, because you're not, like I say, you're not giving a big bolus of proteins. You're giving one, you're asking the cells to make one protein. So it would not be hard to piggyback a dozen messenger RNAs into a virus and make antibodies to a dozen viruses. Okay, monoclonal antibodies. Okay, if you were alive in the 1970s and 1980s and you watched the evening news, you would have heard the media talk about the new magic bullet. The scientists have developed a magic bullet. They were talking about monoclonal antibodies. This is kind of the coming out party for monoclonal antibodies. And everybody knows that antibodies are molecules that our immune system produces to fight foreign invaders. And this is what an antibody molecule looks like. It looks like somebody standing up, putting their hands up, and the binding sites to the foreign protein are on the tips, the hands. Okay? So before we had monoclonal antibodies, we would inject animals with the antigen, the protein that we wanted, and we would take the serum, because the antibodies are in the serum. In fact, we made products out of that. And if you're old enough to remember diphtheria days, they made a horse antitoxin. And you could use that in humans for a little while until the humans made anti-horse antibodies. But it worked enough to save the kids from having heart damage. So antibodies have been an important reagent in the laboratory, in therapeutics, and in diagnostics as well. So in the 1970s, some British doctors decided that they needed to have a pure antibody, an antibody that only had binding to one antigen and had the same binding sites to one protein. And they knew you could immunize a mouse, and you could take the cells that produce antibody out, which are the B cells. Activated B cells are called plasma cells. They're the ones that make antibody, the plasma cells. So you can take them out and you can put them in culture, but because they're normal cells, they don't divide and grow in culture. So these guys also knew that there was a cell that would grow in culture and produce antibody, and that cell is known as a myeloma cell. And everybody here should have heard about myelomas because they're a common human and animal cancer. So they decided that what they needed to do was fuse the normal cells with the tumor cells. So that would endow the hybrid with the ability to produce this antibody and ability to grow in culture, because tumor cells are immortal and divide rapidly. And they worked on that for a long time, and they came up with a chemical process that would allow those cells to fuse and make hybrids. And once you have hybrids, you can take one cell at a time and look at it and see what antibody it's producing, and then you can scale it up and produce the antibody, and that's your monoclonal antibody. Okay, so now we have a population of antibody with the antigen binding site, the binding site, all the same, and you can make tons of it in culture. But now what we have is a mouse antibody, okay? And like I said, the horse antibody, humans make antibodies to it, so it's only good for a couple of treatments. And the same here. In fact, when I was at the National Cancer Institute in the early days of monoclonal antibodies, that's all we could make is mouse antibodies. And we had cancer patients that we wanted to test these antibodies on. we selected a group of cancer patients that made tumors with unique proteins on them. Each patient had a unique protein on their tumor, and we made antibodies to that protein on their tumor. And we would grow them up and inject them into the patients, and there would be a response. We could inject 2 times and get a response, and then after that, the patient would get sick from getting injected. So for most of the years of monoclonal antibodies, we had only mouse, so not a lot of activity. The silver bullet that they talked about wasn't here yet. But we got smart after about 20 years. We got a lot smarter about recombinant DNA. In fact, the hybridoma, the fusion of the mouse and the tumor cell, is a primitive form of genetic engineering. But we got better with it, so after about 20 years, we were able to take the gene that encodes for the binding site and splice it onto a gene that encodes for a human antibody. And now, for the last 20 years, we have been making humanized antibodies. And that's what sent the monoclonal antibody business skyrocketing. And for this pandemic, this is one of the first times a lot of people ever heard of monoclonal antibodies. We got an antibody to the anti-spike protein from Regeneron. We got one from Eli Lilly. We got one from GlaxoSmithKline. And we had an antibody from Genentech that was approved previously for rheumatoid arthritis. So these are the antibodies that we use. The problem being that you have to get the monoclonal antibody before you get very sick. Because once you get too sick, your cells are already infected with the virus, and the antibody cannot block the virus from infecting those cells. They're already infected. So it didn't pay off as big as we thought. I thought this might be the cure for the virus, but people don't get treatment fast enough. And that's why the new pill isn't going to work very well either, because you have to get treatment, you have to use that really early before the virus gets in all the cells. Because once it gets into the cells, it can affect adjacent cells without being seen by antibodies. Okay, finally, cytokine. This is the big story of the night, and I'll try to make it as simple as I can. As everybody knows, you get sick from COVID. You don't feel very sick at first. You get a little bit sicker, and most people get better. But some people progress into a hyperinflammatory phase known as a cytokine storm. The cytokine storm works something like this. The cells get infected by the virus, and the cells send out chemical signals for help to the immune system. And those signals that the cells send out are called chemokines. And those chemokines bind onto receptors on immune cells. And it activates immune cells, which makes immune cells angry. We call them angry, but they can divide and they start producing proteins to communicate with other immune cells. And those proteins are called cytokine. And that's where the term cytokine storm comes from. So tonight I'm going to talk about one interaction between a cell receptor and a chemokine. Okay, the chemokine, like I said, comes from the infected cells. That's the message from infected cells that they need help. And the receptor is what it binds to activate the cells. Okay, I'm sure you wonder why I'm talking about HIV here, but there's a little company in Washington State that has an antibody, a monoclonal antibody, a humanized monoclonal antibody that binds to the CCR5 receptor, the receptor that's on And this particular receptor is going to be on CD4 T cells. And those are the cells that HIV infect, is the CD4 T cells. And if you remember about HIV, they infect those cells, the cells die over a period of time, and your immune system diminishes, slowly diminishes, until you start getting opportunistic infections and cancer, and you die. Okay? So this little company has an antibody that binds to the CCR5 receptor, which just happens to inhibit the binding or the internalization of the HIV into CD4 T cells. And they've been working on this antibody, with this antibody, for about 7 years to take it through all the different steps to get FDA approval. As the pandemic was starting up, they were finishing up their phase 3, which is the final phase of clinical trials, and starting to write up their data. But like everybody else, they decided to test their antibody on COVID-19. And look at this write-up here. It says, inhibits HIV without blocking the natural activity of CCR5 in vitro, which is in a Petri plate. So they didn't think that this antibody really did anything spectacular to the immune system, but they tried it, and sure enough, it blocked at least enough binding of the CCL5, which is the chemokine, to immune cells, okay? And it modulated the immune response, so it tamed down quickly, almost overnight, the cytokine storm. Patients who were on ventilators came off ventilators within 24, 48 hours. The clotting, which has been a big problem in the COVID infection, stopped. The immune system became more normalized and continued to fight the virus, but in a more calm way. So this was interesting, because this little company that was going after one product now has an antibody which is an immune modulator. And it's known that CCR5 is present on other cells, on cells other than immune cells. It is present on immune cells, but it's also present on many cancer cells. Okay? And the thought is, wow, cancer cells divide quickly, kind of like an activated immune cell when it binds to the CCL5. And cancer cells metastasize, just similar to how the immune cells start to mobilize. So they decided to go into a cancer trial real quick, and they picked a group of cancer patients that were very sick and had no other real method of treatment at that point. And they treated those patients with their monoclonal antibody, thinking that they could measure in those patients the slowing of the metastasis. And not only did they see total blocking of metastasis, but they also saw the tumor start to shrink. Okay? And because this immune modulator seems to be active in many different ways, they started going off after other things, okay? They're still going after COVID-19. They're in phase 3 clinical trials right now. This is something that really would save a lot of lives if it could win approval. They're still doing their HIV. They did this quick and dirty cancer trial, and now they are doing a basket trial, which means they're taking several different types of cancer and looking at them at the same time. Okay? They also think that this might be good in things such as MS, maybe Alzheimer's, anything that has an immune component, or that the CCR5 receptor might play a role. Okay? And we'll look at that quickly one more time. one of the reasons that the tumors started to shrink, possibly, was that the CCR5 receptor is present on endothelial cells, which help to produce veins and arteries, and tumors need veins and artery production to survive. And if you're blocking it, if you block the CCR5 in a lymphocyte, it kind of goes back to normal. It repolarizes, they say. So it's possible it slows the growth of cancer cells as well. So this, to me, is one of the major breakthroughs of the pandemic. And now I have a question for everybody. Who would use ivermectin if they were sick? Just say yes or no.
Sick with what?
No.
Sick with what?
With COVID-19. Some people would and some people wouldn't, right?
That's what the doctor said.
You would do what the doctor said?
Yeah.
Okay. Well, there's been clinical trials done on ivermectin all around the world. And I know you can't see that, but these are the different countries that some of these trials came from. This is out of the Japanese Journal of Antibiotics. And I broke out the data a little bit. Mortality, right here, 3.3% as opposed to 18.3%. Mortality, the national mortality in this case was 2.1%. With ivermectin, it was 0.59%. Hospital stays significantly reduced. Preventive, some of these were preventive, prophylaxis, right here. Okay, so we have a lot of data that says it probably does work, despite laughing at all the people who are going out and buying it. So the conclusion of this article was that with moderate certainty, evidence finds that large reductions in COVID-19 deaths are possible using ivermectin. Using ivermectin early in the clinical course may reduce numbers progressing to severe disease. The apparent safety and low cost suggests that ivermectin is likely to have significant impact on SARS-CoV-2 pandemic globally. The FDA says, we don't have solid evidence right now on the drug. We had hints for a long time on ivermectin, but again, we've had hints of these agents, many of them not panning out. Okay, that means the FDA is not going to sign off on it. And of course, they want you to jump through the testing that they want you to jump through. Merck, which is a company that makes ivermectin, says there is no scientific basis for potential therapeutic effects against COVID-19, no meaningful evidence for clinical activity or clinical efficacy in patients with COVID-19, a concerning lack of safety data. Okay, I would say that's wrong, all wrong. I mean, those results that I showed you are pretty good results. I mean, they have p-values. The statistics are look good on them. I would, if it was me and I was sick with COVID-19, I would take it because of the fact there's nothing else. There is nothing else. Okay, one thing I should point out is that ivermectin is an approved drug in the US and around the world. So doctors have the ability to prescribe an approved drug off-label. And that's what's happening in the US and many other countries, which is a good thing. Okay, this is something to think about. A British trial called Recovery has provided important information about older drugs, finding that hydroxychloroquine, while a steroid dexamethasone could be a lifesaver. And that's the standard of care right now, dexamethasone. It took the mortality rate from about 3-point-some% down to 2-point-some%. But the United States has lagged behind in conducting such trials because of the fragmentation of the healthcare system and the lack of financial incentive for pharmaceutical companies. to continue to do research on old cheap drugs, which is exactly why Merck has this on their webpage, even despite the data I showed you and many other studies that have been done that show positive data. Okay, so the final thing I'm going to say tonight is that the COVID problem has sucked up all the blood all around the country and all around the world, because these people who go in with severe COVID need transfusions. So, if you're able to give blood, please give blood. Tell your neighbors to give blood. Tell your kids, your grandkids, everybody to give blood. And if you live locally, please give it to Lee Health, because the other bus that drives around town, which is called One Blood, they sell their blood out of state. But they sell it to anybody who will buy it, but they sell their blood. So donate it to Lee Health, because that's where the blood helps the local people the most. And the blood problem has been a problem. I mean, there is not blood for people who are coming in serious accidents and have problems in surgery and stuff. So it's a big problem. Okay, that's the end.